So, from this slide on, for the next 3 slides, we are going to go over 3 of the basic circuit elements that was introduced to you in high school, right? The resistor, inductor and capacitor. We will go through the derivations of the current voltage relationships between these and how they were derived, and also to keep in mind that why these were done, right. So, the precursor to actually teaching you circuit elements and having to give you a circuit based flavor for electromagnetic forces and electromagnetic fields is that it largely simplifies the dimensionality of the problem, right. So, electric fields and magnetic fields, like I told you, requires 6 individual parameters Ex, Ey, Ez and Bx, By, Bz, each of which has to be precisely mentioned for every location x, y, z in 3-dimensional space and also at every instance of time, right. So, this becomes a very large collection of numbers to kind of keep track of things, right. So, circuit theory fundamentally improves the situation by saying that let us look at fields that are confined within wires, fields that are confined within elements called resistors, capacitors and inductors, and actually try to bring the situation down to the dependence on just time, right. So, we are completely removing the dependence in space, somehow absorbing it into simple terminal voltage and terminal current relationships, so that we are actually able to manage the complexity which otherwise can become unwieldy, right. So, the resistor drawn in circuit models as the zigzag line, right, is a symbol for the resistor and is a very popular and most basic element in circuit theory. And we are going to look at the relationship between the terminal voltage and the terminal current. Right. Okay. So, it says that the potential difference between the endpoints of the resistor when divided by this parameter called resistance R gives us the flow of current through this element, right. So, let us break down both the relationship and each of these variables. Okay. So, let us start with current that is flowing through the resistor, right, is defined as the flow of charges. Okay. So, if we were to take in reality a piece of say metal, a cylindrical piece of metal, and we apply a certain voltage across it, right. We assume that the conductivity of this wire is not infinite and that there is some finite resistance to the flow of charges. We want to establish this relationship, which is known as the Ohm's law, right, from some first principles, right. So, we start with defining the current as flow of charges, and if I wanted to bring it out mathematically, I say that if I have a certain area A and if I have charges breaching this plane of area A, right, this disk, I essentially keep count, right. I keep count of all of these charges. Remember, they are quantized, right. So, some number of electrons that is flowing through this area. If that charge that is flowing through that area is delta q in a given time slot, right. So, say from one instance of time to a delta t later, I just keep track of how many charges are breaching this plane, and if I do a sum total of all the charges and divide that by the delta t, in the limit of delta t going to 0, we say that the instantaneous value of current through this area A is dq by dt, right. So, we have to somehow use this definition of flow of charge in the wire and come up with the Ohm's law relationship, right. So, the way I do that is I consider a small volume right. So, the cross sectional area of the wire that I have chosen is A, and then I take a small sliver or small length delta x, and I consider the charges that are contained in this volume, and I make a claim that all of these charges that are moving, say, from left to right will breach the back side of this volume, right, as indicated by the arrow, in a short time delta t, right. So, the value dq is all the charges that are there, the free mobile charges in this volume. So, which is essentially n times a dx times the charge of one electron, right. So, n here is the charge density, right, not the number of electrons, but the number of electrons per unit volume, right. So, the charge density small n multiplied by the volume and then multiplied further by the unit charge, right, gives us the net charge that is moving in a time delta t, right. So, if I were to divide by dt on both sides, I essentially get the relationship that I is n a e times u, right. So, I cannot expect all of the electrons to have the same velocity, but some mean velocity, right, which I am calling u with the angular brackets around it. Okay. So, we are saying that if I can somehow find the mean velocity of all the charges, then I can somehow get the current that is flowing through this charge. So, what is causing these electrons to move in the first place? It is the potential difference across the wire, which we say establishes a field within the wire, an electric field, which applies a force on each of these electrons, and these electrons can accelerate, right. So, you may wonder, right. So, forces caused acceleration, which means that this u must be ever increasing, right. So, the current through a conducting wire should just keep increasing with time if there is a constant electric field. But we do not see that, right. In reality, what we say and explain this by is that these electrons are not free to move, but they undergo several collisions with the constituents of the wire and are interacting with other electrons themselves and end up having a fairly rather chaotic motion, right. So, if I were to look at a single electron's motion, it may look very chaotic. Okay. So, each of these points where I show a turn or a change in direction is a collision event where the electron has interacted with another particle and has changed its direction of motion, right. So, the electron is sort of chaotically moving, and in the presence of an electric field, it is expected to only move in the direction of the force experienced by this electron through the electric field very slowly, right, because it is spending a lot of time going the wrong way, right, because of an interaction with the host, which is the particles of the wire, right. So, in order to bring out this mean velocity of the electrons, we are going to say using Newton's laws that the mean velocity u is essentially the average Okay. So, this is your famous equation for motion, right. So, where ui is the initial velocity. So, I will indicate this path as A, B, C, D, E, right. So, ui is essentially the velocity at say A, B, C, D or E, right. So, those are the n different summation points. So, it is the starting velocity at each of A, B, C, D and E, and then added on to that would be the acceleration, right. So, the acceleration would be changing the velocity of the electron, but each time the collision happens at B, C, D or E, it is sort of like a reset button, right. The electron completely loses its memory of how fast it was going and in which direction it was going, and it's sort of like a complete reset, right. It's very hard to predict in which way and which direction and how fast it's going to go after every collision event, right. So, we assume that these initial velocity vectors ui is essentially scattered uniformly around the 2 pi, right, when looking at several scattering events put together. And so, we can say that the vectorial sum of all of these initial velocity vectors is 0, right. This is also to say that when there is no electric field, that there is no net motion of electrons going either way, right. So, you just have random Brownian motion, and the average of all these motions keeps all of the wire, the resistive wire charge neutral, right. So, it is only the electric field that gives them a reason to be moving towards a particular direction, right. So, for an electron to be moving to the right, we would need the field to be oriented to the left, right, and hence the only term that we have in the average velocity expression is that caused by the acceleration term, right, and this we essentially pull out all the constants So, this term in the bracket is what we call the mean scattering time. Okay. So, I am using the character tau to explain that there is a mean time, right. So, the time it takes to go from A to B is different from B to C and C to D and D to E and so on, right. So, there could be different times between any collision event, but it is expected that for a certain charge density and a particular wire of some material that is chosen, that there is something called a mean scattering time, right. So, now we have actually found the average velocity with respect to some constants that is dictated by the resistor itself, right. And so, we can say that my current I is N A E right. So, I can combine all of this to say that it is right. So, the term in the bracket in the end is called the conductivity. Okay. And you may have also been introduced another term called resistivity, which is the reciprocal of conductivity, right. So, resistivity rho is 1 over sigma. Okay. So, a more popular way is to rearrange and take the area to the left hand side and actually say that the current density is proportional to the electric field, right. And the constant of proportionality is the conductivity of the wire, and it depends on the charge density n, the value of charge on a single electron E, the mean scattering time, and the rest mass of the electron. Okay. So, this is what we call as the point form for Ohm's law, where it says that you can define this for even local positions, right, within the wire. Nonetheless, in this example where we have taken a uniformly conducting wire of cross section A and some length L, right, we expect the field to be uniform through this wire, and hence the current density is also going to be uniform, right. But nevertheless, we call this as the point form of Ohm's law. If it is still not very apparent as to how this actually relates to Ohm's law, which seems to be relating voltages and currents, we can quite simply look at that also. So, taking this equation, we have I equals one over rho A E, and electric field can be written as the voltage by the distance L, right. So, I am applying a voltage between the end faces of this conducting wire, finite conducting wire. So, the electric field that is established between these two faces is simply the voltage divided by the length of the wire, and you might have also been taught a relationship that combines the geometric parameters of the wire and the resistivity, and this is what we call as the resistance. Right? In fact, it is the inverse of the resistance, right? So, R is rho by A, right? So, this is how you can go from the point form to the more popular V equals IR for the Ohm's law, right. So, this is how you were perhaps taught the derivation of Ohm's law for a resistor.